Let's walk through one of the common questions in paper 2, AQA A-Level chemistry. In this question, they provide you with different spectra for an IR and carbon-13 and proton NMR for a compound, and they ask you to deduce the structure of that particular compound. So the first question here, they provided you with the IR for the compound and ask you to identify the bond that causes the absorption at 1725. So when you look at the data booklet, this is going to be a carbonyl group. So when you have this sharp peak at 1725, this is always going to be a carbonyl group. The second question, they provided you with the carbon-13 NMR, and first question is to ask you how many different carbon environments are there in the molecule. So you simply just count the number of signals in the carbon-13 spectrum, and when you do the counting, you're going to find there are 7 different signals, so there are 7 different carbon environments. State the type of carbon environment that causes the peak at 174 ppm. And then you need to use your data booklet for carbon-13, and you're going to find that this peak here at 174 is for a carbonyl group coming from either an ester or an acid. However, here when you look at the IR, there is no peak for the OH, so we don't have an acid, we only have an ester, so you have to state that this is for an ester. So it's a carbonyl coming from an ester. Also, there is another peak here at 210 part per million ppm from the carbon-13. This is going to be used later when you deduce the structure of the compound, and this is for a carbonyl from a ketone. So just remember this because you're going to use it later. So we know now we have a carbonyl from an ester and we have a carbonyl from a ketone. Then they provided you with the table for the proton NMR with the integration ratio and the splitting pattern, and explain what can be deduced from the splitting pattern and chemical shift values for these two peaks, 4.10 part per million and 1.26 part per million. You're going to use the data booklet to answer this. So first of all, you need to identify the type of proton. Looking at your data booklet, you're going to identify the first one, which is the 4.10 here. So this is, there are two protons, but the type of proton first is going to be an R, C, O, O, and C hydrogen. So this is the type of proton where there is a single bonded to an oxygen coming from an ester. This is coming from the data booklet. And then when we look at the splitting pattern, you're going to find that it's aparted, which means that the neighboring carbon has 3 protons. So there are CH3, and then we have a CH2 because the integration value is 2 protons, and then you have the oxygen and then the carbonyl group, so or the ester group. So this is the 2 protons, and this is the neighboring 3 protons from the carbon. So you have to refer to the presence of neighboring 3 protons. Then looking at the peak at 1.26 part per million, when you refer to your data booklet, you're going to find that it's either 1.26, it's going to be an R2CH2. This is referring to the data booklet, meaning it's coming from a proton that is next to a carbon, another carbon. And then you would look at the splitting pattern. So it's a triplet, meaning there is, first of all, it's going to be 3 protons. So there are 3 protons here. So when you look at the, there are 3 protons and it's triplet, meaning there are neighboring 2 protons. So we have a CH3 and next to it there is a CH2. So this is the CH3 here, which are the protons which give you the signal at 1.26, and neighboring to it there are two protons. So you have to say there are two neighboring protons. So the part of the structure, if we combine these two signals, it's going to be CH3, CH2, and then oxygen, and then a carbonyl group. So this is the part of the structure that give you these two signals. And then deduce the part of the structure that causes the peak at 2.19 part per million. When you refer to the data booklet, 2.19 is must be coming from a hydrogen on a carbon next to a carbonyl group. And referring to the data booklet, it's going to be the RCO and then CH. So, and then 219 here, there are three protons, which means that it's going to be three protons here. So it's simply a CH3 next to a carbonyl group. So this is the part of the structure that causes that signal next to a carbonyl group using the data booklet. Then they give you another proton NMR. They show you the spectrum itself for the NMR, and they ask you to suggest why it would be difficult to determine the structure of this compound using this spectrum without the information in table 2. There are two main issues here with this spectrum that will not help you to deduce the structure. The first one here is this peak here between the 2.5 and 3, which are the two peaks at 2.56 and 2.60. There is an overlap between these two peaks. So there is an overlap between the peaks, which are at between peaks at the 2.56 and 2.6 part per million. And there is another problem here also, which is that there is no integration for the peak. So no integration as well, because we would need the integration to find out how many protons giving each signal. So no integration as well. So you can either mention the first or the second issue, because it's only one mark question. Finally, they ask you to deduce the structure of this compound. To deduce the structure, we know part of the structure, but we need now to look closely at the different signals from the proton NMR. So now you have three signals in the region between 2.19 until 2.6. So these are three signals. So all of these will come from protons on carbons which are next to carbonyl groups. And we know as well that there is two carbonyl groups here, as we can see, one of them coming from a ketone, one of them coming from an ester. So, and then when you look at the two peaks at 2.60 and 2.56, you're going to find that each of these are two protons, and there is a triplet here. So each of these are CH2 next to a CH2. So now thinking about all of that and combining all of this, you're going to find that the structure of Z will be CH3, CH2O, and then the carbonyl. This is the ester, the first part we deduced. And then we must have two CH2 groups, and each of these have to be next to a carbonyl group. And then we also deduced that there is a CH3 next to a carbonyl group, because there is a singlet for this peak, which was at 2.19. So this is the final structure of Z. Remember that even if you don't get the final structure of D, you still, it's only one mark, but your analysis of the different peaks and the integration and the chemical environment for each of the protons or for each of the carbon will give you a lot of marks from the